Now, I promised we would work one of the free response questions. So let's go ahead and take a look at it. Here's the problem. It's from the 2022 test, problem number 1. 2 blocks are connected by a string that passes over a pulley as shown above. Block 1 is on a horizontal surface and is attached to a spring that is at its unstretched length. Friction forces are negligible in the pulley's axle and between the block and the surface. Block 2 is released from rest and moves downward before momentarily coming to rest. And then it gives you some figures. The spring constant, the masses of the 2 blocks, and the height change of block number 2 before it comes to rest. They said there's no friction here. There's no friction along the horizontal surface. They said that the spring was unstretched. It was not compressed and not extended. And you knew all of that because you read it carefully or you read it aloud. Block is released from rest and it moves downward before momentarily coming to rest. So the first thing that I advise you to do is to pause the video and ask yourself, okay, what is going to happen when we take our hand off of this mass and let it start to descend? Go ahead and pause the video and I'll wait. Okay, well, you know intuitively what's going to happen. The mass is going to start coming down. It's going to pull the string. It's going to pull this mass and start stretching the spring. And at some point, it's going to get low enough that the restoring force on the spring is going to get big enough that the spring is going to say, I'm not letting you drop any more than that. And it's going to stop the downward motion of mass number 2. And then mass number 2 is going to do what masses on springs do. It's going to bounce up and down. I think. Doesn't that look like that's what should happen? So let's see what they're asking of us. They say block number 2 starts from rest and speeds up. Then it slows down and it momentarily comes to rest at a position below its initial position. In terms of only the forces directly exerted on block number 2, explain why block number 2 initially speeds up, and explain why it slows down to a momentary stop. And they give you more space than this for your explanation, but I compressed it for this video. So they say, in terms of only the forces directly exerted on block number 2, explain why it speeds up and then stops at some point. I think we mostly got that figured out. What are the forces on block number 2? Well, we know there's a downward force from gravity, and that's mg. So it's m2g. And we know there's an upward force, and that's the tension in the string. So the tension in the string is pulling it up, and that same tension is pulling mass number 1 that way. That's how strings work. Remember? If you have a ceiling up here, and you have a mass m hanging from a string, it's not moving. That means the vertical forces on the mass are balanced. So what are the forces? There's a downward force of mg, and there's got to be tension in the string. So the upward force has to be mg. That's the tension in the string. And tension in a string pulls away from where it's attached to objects. So this string right here is pulling up on this mass, and it's pulling down on the ceiling. But the ceiling isn't moving. When we're holding this mass in place, when we're holding M2 in place before we let go of it, the spring is in equilibrium. Nobody's pushing mass 1 around, and we're holding this, so there's actually no tension in the string. But we know that when we let go of mass number 2, gravity is going to move it down, and that's going to start to pull the spring, and the spring is going to try and pull it back. So this fight between gravity pulling it down and the spring trying to pull it back is going to cause some tension in the string, and the tension will be the same. This is going to be T, and this is going to be T. And that's how strings work. You learned that back doing force body diagrams for things suspended on cables. Okay, so how are we going to explain this? Initially, gravity is putting this force heading downward, and the initial tension in the spring is 0. So the vertical forces on the mass are unbalanced, and the mass will accelerate downward. But as the mass accelerates downward, it's moving. That's what acceleration means in this context. So as it moves, it's going to stretch the spring. And eventually the restoring force of the spring is going to get big enough that it'll be pulling back on the string, and the tension holding M2 up, this tension right here, is going to grow until it matches this. And then the net vertical force on the box is 0. And does that mean the box will stop? No. It means the box will stop accelerating. Right? Because something that has no net force is either at rest or it's moving with constant velocity. So the mass is going to accelerate downward until as it moves and the spring gets stretched, the restoring force matches the gravitational pull, and then as it continues to move, the restoring force will get greater than m2g, and there will be a net force upward. So whatever downward velocity the mass has when these two forces hit the same is going to be eaten away by that upward acceleration, and that upward acceleration will eventually cause the mass to stop moving. So I want to draw a chart and see what's happening here. It's not that hard. This is time, and what we're going to put up here is the acceleration of the mass. We have the wall and the spring, and the first mass here goes around the pulley and attaches to the second mass, and we are holding the mass right here, and then we let go of it. So they wanted us to look at the net force on mass 2. So what are the forces on mass 2? Well, it's gravity in the downward direction, that's m2g, and the tension force from the string. You remember tension forces, right? If you have a ceiling here and you have a mass hanging from a string, the downward force from gravity is mg, but the mass isn't accelerating down or up, and the only other vertical force on the mass is the tension in the string, so the tension in the string is mg. And the tension in the string applies the same force on both ends of the string. So if this string is pulling up on the mass here, it's pulling down on the ceiling here. In our current situation, our mass is not at equilibrium because we were holding it here. But let's say it were. Let's say we're just hanging there. Nobody's touching it. The spring is stretched a little bit. There's no net vertical force. That means gravity is pulling down with mg. The string is pulling up with mg. And if the string is pulling up with mg here, it's pulling this way with mg on the block and the spring, because that's how tension in strings works. It pulls the same on one end as it does on the other end. Okay? So let's go back to here. So the net force on the mass, and we'll say y goes in the positive direction up. So the net force on the mass is the tension in the string, which is in the upward direction, minus m2g, because that's in the downward direction. And the acceleration is proportional to the net force, just because F equals ma. Okay? So, at the very beginning, the string is unstretched, and we're holding mass number 2, so there's no tension in the string. So this is 0, the tension in the string, and the net force is negative. So the acceleration is negative. Okay, so we'll put our 0 here, and we'll start out with the negative acceleration. And the block is going to descend, like we intuitively know it's going to descend. As it descends, it's going to pull mass 1 this way, stretching the spring. The spring is going to start fighting back with a restoring force, and that force is going to get transmitted through the string, and the tension in the string is going to get bigger and bigger. And as this gets bigger, the net vertical force on the mass is going to get more and more positive, more and more in the positive y direction. So the net force started out at negative m2g, but as the mass moves down, the tension force above m2 gets bigger, the net force is less negative, and the acceleration is less negative, and it's going to somehow head in this direction, less negative. As the mass continues to come down, the spring gets stretched more and more. Its restoring force is going to get bigger, pulling this way on M1, which is going to increase the tension in the string, and eventually the tension is going to equal M2g. The net force on the mass will be 0, and the acceleration will have made it all the way up to 0. So here we are here. The mass has descended enough that the spring's restoring force matches gravity's force. There's no net vertical force, and the mass stops accelerating downward. But does that mean it's all the way down as low as it's going to go? Its acceleration has stopped, but it still has some velocity, doesn't it? Let's take a look at this animation that I showed at the end of the third video on springs and simple harmonic motion. Here's our spot going back and forth and back and forth. It's a mass on a spring bouncing left and right, and we know that when it's at its extent, at the ends of its amplitude, the spring is either maximally compressed or maximally extended, and so the restoring force is the greatest. And when it's passing through the middle, when it's at its equilibrium point, the spring is neither stretched nor compressed, and the spring is not putting a force on the mass. The net force on the mass as it crosses the origin is 0, but it's still moving because it was accelerated. In fact, at the origin is where it has its greatest velocity. And then it heads out to one of the ends of the amplitude again. And as it heads out toward the end of the amplitude, the spring is getting more and more compressed or more and more extended, and the restoring force is greater and greater. And if the force is greater, the acceleration is greater. The change in velocity is greater, and it gets to a point where the velocity drops to 0. And it drops to 0 at the point at the end of its amplitude where the acceleration is the greatest. But the point here is that when it passes the origin and the spring is at its equilibrium position, there's no acceleration, but there is velocity. So if we put the velocity on our chart, the velocity is going to start out from 0 when we let go of the mass. But with a downward acceleration, the mass is going to pick up a velocity in the downward direction, just as we expect it to do. But as it drops, the acceleration gets less and less. But as the acceleration gets less and less, the velocity will keep increasing, but the rate at which it increases will slow. And when the acceleration hits 0, that's like the mass at the origin of our animation. There's no more acceleration, but the velocity is high. In fact, it's at its maximum. And then as our mass continues to drop even farther, and the spring gets stretched even more, the restoring force goes up, the tension in the string goes up, the net force is now growing above 0, the net force is in the upward direction, and our acceleration is moving upward. And if the acceleration is in the upward direction, that means that the negative velocity is going to be slowing down, and eventually the velocity gets to 0. And when the velocity is at 0, the mass has come to a rest. The acceleration happens to be at its maximum point. Just like in our animation, when the velocity hits 0, at the end of its amplitude travel, the spring is maximally stressed, the acceleration is maximum, and the velocity is 0. You knew all this. I just hope I didn't confuse you by drawing the chart. So all this time that we've been looking at, there's been a velocity in the negative direction. Sometimes smaller, sometimes bigger. The velocity comes back to 0, and the mass stops moving when the velocity hits 0. But the velocity has always been in the downward direction. The mass has dropped at different speeds and different accelerations, down, 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 and then it stopped. And they want to know how far it dropped when it finally came to a rest. So this whole thing is a really technical explanation of what you knew already. You let go of the mass, it's going to start dropping. The spring is going to pull on it. The spring is going to say, "Nuh-uh, I'm not going to let you drop anymore." And the mass is going to stop. And then it'll start coming back up. So what did they ask? They said the block starts from rest, speeds up, slows down, momentarily comes to rest at a position below its initial position. Duh. In terms of only the forces directly exerted on block 2, explain why block 2 initially speeds up and why it slows down to a momentary stop. We have it all. We just have to put it into words. It's because when we let go of the block, the net force on the block is m2g in the downward direction. And so the block will accelerate downward. And right when it starts moving, the tension force in the string, which is the other component of the vertical forces on the block, will get greater and greater. Eventually the net force will be 0, and the acceleration will hit 0, and the downward velocity will be at its maximum. And as the block continues to drop, the tension force overwhelms the gravitational force. There's a net upward acceleration, and the downward velocity of the block gets eaten away until the block stops moving. And I believe that's all you have to say. Okay, let's try this again. How we're going to write it. In terms of only the forces directly exerted on block 2. And I'll show you something about this too. Explain why block 2 initially speeds up, and explain why it slows down and momentarily stops. And we already know this. Here's our spring. Here's block 1. The string comes around, and here's block 2. The forces on block 2 are the force of gravity and the tension in the string. At first, we're holding the block, preventing gravity from pulling on it, and the spring is at equilibrium. When we let go of the block, gravity takes over to start to pull, but with all this at rest, there's no tension above. So we have a net force downward on the block, and the block accelerates downward because of the net force. As the block goes down, mass number 1 moves this way, the spring gets stretched, and the spring starts to pull back, the restoring force, proportional to the amount of stretch. Ergo, the tension in the string above the block increases, the net force is less on the mass because gravity is being opposed, the block's acceleration slows, and this block can't descend forever because the force in the spring is going to get higher and higher. So eventually the force in the spring matches gravity, and as the block continues to descend, the force from the spring surpasses gravity, slows the block, and the block stops. Now, if you knew no physics and you just watched that happen, you would say, duh, but they just want you to explain it. They also said, in terms of the force directly exerted on block number 2. So they want you to talk about gravity. What's attached to block number 2? Those are the forces directly exerted on block number 2, and the tension in the string. Those are the two forces, and you have described what happened. So let's go to the scorer's guidelines and see what they say. They say, well, you get 1 point for relating the net force to acceleration or change in velocity. We did that. We said the net force in the downward direction is m2g minus t, and the net force is related to the acceleration. It also said you got a point for a correct description of the relative magnitudes of the tension and the gravitational forces during the motion. Well, we did that. We talked about how the tension starts out less and gravity starts out more. And as it descends, the tension becomes more than gravity and slows and stops the block. Then they had a special note. They said the point is not earned if the spring force is explicitly stated to be a force directly acting on block number 2. They don't want you to say that if here's block number 2, that this is gravity and this is the spring, because this is the tension in the string. They asked for what forces were directly acting on block number 2. And then they give an example response that they think is great. Quote, the direction of the acceleration and the direction of the net force are the same. The block speeds up when gravitational force is greater than the tension, and then slows down because the tension becomes larger than the gravitational force. Okay, did that. Next, derive an expression for the distance delta y that block 2 travels. This is going to be easy now that we understand everything that's happening, because you know how to start every equation. Oh, let's talk about this first. This is a spring. Okay, and what do springs do? They put forces on masses. They store potential energy. They store potential energy when they're compressed or extended. This has to do with gravity. Gravity will accelerate masses, right? It'll slow them down. But there is also gravitational potential energy. This is energy. This is energy. It sounds like there are clues all over the place that we should use an energy equation to answer this problem. So let's do that. And how do we always start out an energy equation? We say the energy initial equals the energy final, and then plus any work on the system from external or non-conservative forces. But we don't have any of those here. Gravity is a conservative force. The spring is a conservative force. We don't have any friction stealing force away from us, so we don't have to worry about that here. We can write it into our equation, so we never forget to put it there, but it will turn out to be 0. And then what's the next thing? We always write down. What is the initial energy? That's the spring potential energy, which I always write down even if there's not a spring, plus the gravitational potential energy, plus the kinetic energy. And I'm going to leave out the work here. So these are the initial, and this is the final. The spring potential energy that's final, plus the gravitational potential energy that's final, plus the kinetic energy that's final. There's our equation. Now all we have to do is fill it in. So let's take a look at this. If we're talking about gravitational potential energy, we have to have a reference plane, okay? I'm going to pick it down here at the bottom of where the mass descends to when it stops. So we'll say that's gravitational potential energy equals 0, which means that up higher at delta y, the gravitational potential energy is mgh, which in this case is m2 g, and the h is the delta y. Now, as we know, I didn't have to select this as the reference plane. When you're talking about something moving up or down, the only thing that's important is how far it moved, up or down. So in this case, it looks like we're going to start with the gravitational potential energy of mgh, and when the block stops, the gravitational potential energy will be 0. We could have said that it starts with the gravitational potential energy of 0 if we put our reference plane there, and when the block stops, the gravitational potential energy would be negative mgh. And we get the same exact answer, because at the end, it's mgh less than it was at the beginning. And that works for any of your problems. So let's draw this in now. At the beginning, the spring potential energy is 0 because the spring is at equilibrium. So this is 0. We know that the kinetic energy is 0 because nothing's moving when we're holding the block before anything happens. So this is 0. And we also know that the kinetic energy, when the block stops moving, the kinetic energy final is 0 because they asked about when the block comes to a stop. So the gravitational potential energy to start, we said was going to be m2g times delta y, because it's mgh, because our reference plane is down where it stops. So the gravitational potential energy is the mass that's moving times g times the h, which is delta y. That's how far it moves before it stops. That's what they wanted to know. How far did it move before it stops? The gravitational potential energy when it stops is 0. We lost m2g delta y of gravitational potential energy as the mass descended. And the spring potential energy, well, that's 1/2 kx squared. That's our equation for spring potential energy. And what is it here? Well, that's 1/2 times k sub naught, which is our spring constant for this spring. And what is the amount that the spring stretched? Well, the amount that the spring stretched is just the distance that mass 2 descended. Okay, that's delta y. So that's delta y squared. All right, so let's go ahead and solve this simple puppy here. We have m2g delta y equals 1/2 k sub naught delta y squared. Let's take a delta y out of each side. m2g equals 1/2 k sub naught delta y. And what are we looking for? Oh yeah, we're looking for how far the block fell before it stopped moving. That's delta y. Okay, let's do what Steve likes and do it one step at a time. Let's multiply both sides by 2. 2m2g equals k sub naught delta y. I'll keep it on that right side. And so delta y equals 2m2g over k sub naught. And there's the answer to that question. And moving on. But oh, wait, you say. Wait, it was that easy? We had our equation and 4 of the items were 0, and we just equated these two and got our answer? Why, you say, did you take me through all of that physics and all of that springs and accelerations and velocities? Well, just so you would understand everything so incredibly clearly, and the next problem would be trivial. All right, what's the next question? Indicate whether the total mechanical energy of the block spring Earth system changes as block 2 moves downward. Okay. What is the total mechanical energy of the block spring Earth system? We talked about this extensively in the playlist on energy and work. The total mechanical energy equals the kinetic energy and the potential energies. The gravitational potential energy and the spring potential energy. That's the total mechanical energy. Well, the total mechanical energy, did it change? It didn't change. In fact, we could write this down because we knew it didn't change, and that's how we were able to equate the initial energy with the final energy. And it didn't change because there were no non-conservative or external forces. So that's easy too. No, it didn't change. And why didn't it change? They want an explanation too. The reason is that the only forces acting on the blocks and the springs were conservative forces. The spring, gravity, no friction. So tell them. Now here's an example answer that they gave in the scoring guidelines. Quote, there are no external forces on the system and no energy is dissipated by friction, so the total mechanical energy stays the same. Unquote. Okay, there's one more thing to do and then we're done with this problem. This one actually takes a little bit of thinking, but we are up to the task. It says, consider the system that includes the spring, earth, both blocks, we've been doing that, and the string, sure, but not the surface. Why not the surface? Let the initial state be when the blocks are at rest, just before they start moving, exactly what we had before, and let the final state be when the blocks first come momentarily to rest. We've been doing that. Diagram A at left, below, this is diagram A, is a bar chart that represents the energies in the scenario where there is negligible friction between block 1 and the surface. And that's what we've been doing. Remember block 1, here's the spring. Block 1 was sliding along a surface while this all was happening, but there was no friction here. The shaded in bars in the energy bar chart represent the potential energy of the spring and the gravitational potential energy of the system, respectively. This is the spring potential energy and the gravitational potential energy. Spring potential energy, gravitational potential energy. Take a minute to orient yourself with any chart. Positive energy are above the 0 point line. Here's the 0 point line. So this is positive this way. And negative energy values are below. So with negligible friction, this is what happened. The spring potential energy started out at 0 because it was in equilibrium, it was unstretched. That's the initial state. In the final state, the spring potential energy had all of the potential energy. The mass was at rest, the spring was stretched, the spring was holding on to potential energy. We knew that stretched or compressed springs hold on to potential energy. That's why we decided to use an energy equation to solve our problem. Initially, the gravitational potential energy was there because the mass was up here and it held some gravitational potential energy, but during the movement it dropped, losing its gravitational potential energy, and the final position, the gravitational potential energy went away. So we are hyper familiar with this diagram A, the left side of the chart. So what do they want us to do? Complete diagram B at right above. Here's diagram B. Oh, look, non-negligible friction. For the scenario in which friction is non-negligible. The energies for the initial state are already provided, right? Same initial state. Shade in the energies in the final state using the same scale as in diagram A. Now what happened in diagram A? Look at the initial in diagram A. They gave us 1, 2, 3, 4 units of gravitational potential energy, and all of that got transferred to the spring. 1, 2, 3, 4. Okay, there's our scale. And then down here, it just says use the same scale, shade if it's positive above or negative below the line, and if it's 0, draw a distinct line like they did. All right, so all we have to do is figure out just qualitatively, not quantitatively, what's going to happen if there's friction. So what is going to happen if there's friction? If there is friction, energy is going to be stolen from us while the mass descends. What's going to happen? Here's our spring. Here's mass 1. Here's our horizontal surface. Mass 2 is heading down with gravity. But now we're losing friction as mass number 1 slides along the plate here. So the work of friction is going to leave our system while mass number 1 is descending on its way to stop. So let's just think about what that means. The energy initial, here's the energy final. The final energy is going to be the initial energy less the work of friction. So we will have less energy to end than we did in the previous situation. Because as friction always does, friction is going to snatch some energy and turn it into thermal energy, and we won't have it for the total mechanical energy. So what does that mean? Does that mean the mass is going to descend the entire delta Y, or less, or more? Well, when it descended the first time, it loaded up on potential energy in the spring. If the mass descends that entire delta Y, the spring is going to get stretched as much as it did the first time, and when the mass stops, the spring is going to have that same amount of potential energy in it. And look what happened. We didn't lose anything to friction, but we had to lose something to friction. So when the mass stops, the spring just can't be stretched that far. The spring has to be stretched less, which means that the mass can't fall that far. So the mass isn't going to fall as far. The spring is not going to stretch as far. The spring is going to end up with less potential energy than in the first time. And look at diagram B over here. The mass is not going to lose all of this potential energy that it had because it's not going to descend as far. And why is that? Because we said that the mass started out with the gravitational potential energy here where it started, and it descended to our reference plane 0. But we already said it can't go down that far because then the spring is going to wind up with too much potential energy, and we have to give something up to friction. So the mass is not going to descend as far, and it's going to still have a little bit of its gravitational potential energy when it stops. And the spring is going to have less of its spring potential energy when it stops, and the sum of these two is going to be less than the initial energy because friction took some. So how might we draw that? Because the mass didn't descend as far, it's not going to lose everything to go from here all the way to 0. So let's say it drops down most of the way but not all the way. And the spring, with its potential energy, it's not going to gain 4 units that it took from gravity. It's going to gain less, So afterwards, the spring is going to be smaller somehow than it was in the initial try over on the left when we didn't have friction. But then we also have that the sum of these two has to be less than the total energy we started out with, because we have to give some up to friction. So what do we know? Let's write it down and then draw it. We know that the gravitational potential energy, which they call potential energy gravity, it starts at 4 and it's going to end above 0. Right? It started at 4 over here on the right, and it's going to go down, but not all the way to 0. And we have 2 that the spring potential energy, which they call potential energy spring, starts at 0. They already drew that for us, but it's going to end below 4 because some energy got lost to friction. And we have that the total of the gravitational potential energy and the spring potential energy when the mass stops has to be less than 4 because we gave some up to friction. So all we have to do is figure out a way to write it, and I'll show you one way. What if gravity drops from 4 down to 1 and the spring climbs from 0 up to 2? Then we have that gravity didn't drop all the way from 4 to 0. We have that the spring didn't climb all the way up to 4 from 0. And very importantly, on the same scale, our total sum of potential energy is less than 4. I only drew 1 unit here and 2 units there. Do you get it? Then you didn't lose any energy to friction. So that's what they wanted you to draw. Now, once again, just qualitatively, you can think about this. What does friction do? Friction slows things down. Friction decreases the amount of motion that's happening. Beforehand, the mass descended all the way down to there. In a second, you could probably come up with the idea that, well, the mass is not going to descend as far because mass number 1 is fighting to move up there. And then you just went ahead and put it in a relationship that they like. Now let's see what the scoring guidelines say about that. Well, the chart that they drew is exactly the one that I drew. Big surprise. And here's how you get points here, what they say. For a final bar chart where both the potential energy of the spring and the gravitational potential energy are positive, greater than 0, you get 1 point. We weren't really at risk of missing that, were we? Because the potential energy of a spring is never less than 0. And for the gravitational potential energy to drop below 0, the mass would have had to move farther. And we just knew that wasn't going to happen. And then, for a final bar chart where the sum of the 2 potential energies is less than 4 units, you get your other point. So it doesn't really matter how you drew these, as long as the sum is less than 4 and they're both on the positive side of the chart. And that's it, ladies and gentlemen. So finally, I read the chief reader's report to see what he thought of how well the students understood the problem and what difficulties they ran into. They didn't like it when the vertical force on mass 2 was related only to the stretching of the spring, and the student failed to mention that it was actually the tension in the string that was pulling up on mass 2. Several students wrongly indicated that the mass would stop descending when the force of gravity was finally equaled by the force of tension. But we know that when those forces were balanced, the downward acceleration stopped, but the mass kept moving until the tension force overwhelmed the gravitational force enough and for long enough to go ahead and stop the block. Students got in trouble if they tried to solve this only using kinematics, only using F equals ma. trying to figure out at every point the force on the mass and the acceleration and its current velocity and how far it would be traveling. It's just too hard. You had to do it using energy. Energy turned out to be easy. Someone got in trouble for forgetting that this was m2 and this is m1. So his solution said delta y equals 2mg over k sub naught. But then he's not really saying that it's m2 that we're talking about and not perhaps m1. And I think the only other thing to point out was in this problem. Indicate whether the total mechanical energy changes as block 2 moves downward. We know it doesn't change, and thus the total mechanical energy doesn't change. But they wanted you to say, well, it's not changing because there are no non-conservative forces. There's no friction, and there's no external forces. That's why. So going back to our solution here, without friction, this is true without the work. And what that means is there was no friction and no external forces. And that's why I usually say, to give us some room, that's why I usually say the initial energy plus work on the system equals the final energy. Because that takes care of friction, which would be negative, or anything else that happens that's not part of the system. And they wanted you to say that in the case without friction, the total mechanical energy didn't change. These two didn't change because there was no friction and no external forces. As always, thank you for your attention. Any comments or corrections are completely welcome. You can put them in the comments or send me an email. And hopefully we will do a few more of these in the near future. Thank you.